Hi. So on to our last speaker now. This is Ajay Sharma of Synopsys. Ajay is going to talk about post-processing techniques to accelerate assertion development to unlock your ABV potential. Ajay joined Synopsys as an application consultant in 2012. Prior to that, he worked for both Springsoft and ICOS. I'll hand over to Ajay now.
Hi, good afternoon, everyone. So today I'm going to speak about predominantly how to use your Assertion-based verification methodology and using the same post-processing techniques within the Verdi environment that we have for debugging purposes. So I won't delve too much about the traditional flows and why you're using assertions. I think Mark's covered that very well as well. I'll spend more time on really looking at the core of the presentation itself. So, typically assertions have been there for a long time. In software world, they've been used, purely to write some kind of a messaging. VHDL always included in assert keywords. It's an open Accelera standard. Okay, so nothing new there. It's basically a conditional statement looking for certain things to happen and pass you a message whenever they do happen. Typical examples, write will follow after 3 reads. If it happened, let me know about it. Or, any of these protocols, interface must follow a PCI protocol, let me know when it happens. Now, traditionally, why do you use this? Because when you start from your concept, your concept is more or less Microsoft Words with some timing diagrams, which then gets fed into various different channels, which are all error prone. So what you were intending as a spec or assuming can be misinterpreted later on. So having a common methodology that can flag those issues out is a must. And that's where assertions come in. So you've got your good, concise description, which is in actually temporal behavior. You can use it for white box error localizations. So immediately flag it out rather than waiting for a propagation of certain issues at the outputs. You can port it very nicely, from block to the system levels. And you can use them in pretty much any of these environments, whether it's formal, simulation, emulation, but also on FPGAs. Okay. So with that comes also the challenges. What are the challenges that if you were adopting this methodology? So these are the few which I've listed down. The intent itself, where shall I put them? Have I done the correct assertion at the correct part of my block? How easy and quick is it to correct the mistakes? If I'm in that learning curve or the development curve, if I make mistakes in my assertions, do I just give up? Or how easy for me is it to debug and move on? Getting some statistics, not only when did my assertions fire, but also an acknowledgement back from the tool saying it is done. It actually did this between this time frame. Debugging them. Assertions are great to flag something has gone wrong. What was the root cause of that particular issue? Where is it originating from? Also something to keep in mind is the speed or the performance. If it's a huge SOC level designs, you're running for simulation and emulation, the runtime does get hampered if you're using tons and tons of assertions. And if you're using emulation or even FPGA prototyping, then resources are a massive issue. It takes up a lot of resources. So we can talk about a traditional view that we have today on how assertions get used. You're typically, your design combined with some assertions goes through any of these flows. It could be any simulator, any emulator, any prototyping solutions, and you can generate something as a waveform file. If it's a waveform file that's kind of open, it's great because then you can port it into a common environment where you can debug this information. Okay, so it doesn't matter what flow you're using for your simulator, emulator, or prototyping. If you dump out an FSDB file, everything can be debugged in Verdi. And you can see either the root cause of your errors coming from assertions, or maybe the functionality of your design is broken, and you can go back and start debugging. Okay, so that's your traditional flow. And having, obviously, like I mentioned, having an independent vendor-independent FSDB format certainly helps. Supports all the standard SVA types, easy to debug. So that's the view you would get out of any standard simulation that you've run. Dump out an FSDB file, start looking at your waveforms and so on. When it comes to emulation, again, most of the vendors today will support the synthesizable subset of SVAs. You can incorporate them in your setup, enable the support, and when it comes at runtime, you have full control on what assertions you need to enable at runtime. So this is coming out of the Zebu emulation system. Again, having a common platform to debug, so dumping out an FSDB file which can directly be read into the Verdi debug environment helps in that case. Moving on to a prototyping board. If you could get out all the information, or let's say the visibility of your design that's running on a prototyping board directly into an FSDB file, then you can gain a lot of visibility out of it. So we actually have a breakout board called Protolink controller. It directly attaches either to a custom board or an industry standard HAFS board. The idea here is basically to take as little as less than 1% of your FPGA resources and still get higher visibility out of your designs. So you can actually get a full visibility out of your board by using the Protolink part. And the idea is to get that signal data into an FSDB so that you can debug directly into Verdi. Okay? Now, this is basically bringing your board from a lab to the designer's desk. But also, within that same environment, you actually have a capability of using assertions to create triggering logic. So whenever those are met, you would actually get an FSDB dump and you can actually see the waveform. So typically in your simulator, for example, you would have, whenever the assertion has been passed, fails, in your proto run or prototyping environment, whenever that assertion has fired, the trigger would fire. You can dump all the FSDB or all the waveform database and import it back into the Verdi environment. Okay? So all three flows that we've seen uses or utilizes the common debug environment. So what do you get out of this common debug environment? So clearly, you will have a standard statistical approach where you can have multiple FSDBs coming from various different runs or various different flows, and you get a good idea on exactly how many properties did I have, how many passed, what time did I have the passing and the failures. You also have this concurrency and temporal behavior or view within your waveform. So this particular sequence or a property in here, what was happening concurrently and temporally, how long did it last before it fired a fail or a pass or so on. And that can be nicely displayed. Moving on, you can also then debug that entire, so you found a failure at a certain point, and we took a notion of how the assertion-based or SVAs were created. Let's say starting from the lower level of your Boolean expressions, building up to the sequence, properties, asserts. So I found a failure in this case. That's coming out of this particular property, which is then coming from this sequence, which is then resultant of this particular Boolean expression to be fails or false. And we also notice here that this particular view has temporal elements. So a clock passage happened at 800. After 2 cycle delays at 1000, this is the values that you're getting on your Boolean expression. And then once you've isolated where this assertion actually is coming or where the failure has come from, you can debug the root cause directly going into this temporal flow view. So this is what I'm debugging. Why is this out going to 5.5? And with a click of a button, I can get to the root cause of why it did go to 5.5. So all in all, having a common debug environment certainly helps, whether it's coming from your simulation, emulation, or prototyping. And this is just going into more detail about the statistics view. So just like I explained, you can have multiple FSDBs, gives you a better overall picture to analyze exactly what's going on. The Assertion Analyzer, again, is a completely different sets of engines than you would have for your standard tracing drivers and loads and so on. Now, just going back, what happens if you have actually made a mistake in coding your assertion? So this flow so far was based on the assumption that you're just running your traditional flow and debugging within a common environment. Now, an issue comes in when I have debugged certain elements and found out that, okay, functionally it's okay. It's actually my assertion that I've coded wrong. And based on that assumption that functionally my FSDB file is actually correct, I should be able to now, get rid of any of the flows that I'm using, directly recode my new assertion, apply it within Verdi's Evaluator engine, and dump out a new FSDB file with the new evaluations based on those assertions. Okay, so FSDB file is golden. Either I'm in a development phase or I genuinely have made a mistake coding some complex assertions. I can just reapply those assertions directly on FSDB file along with the design knowledge, so the bind for the RTLs and so on. And then directly evaluate this FSDB. If I have problems, again, go back, rewrite a new assertion, and follow the flow. And this can be all done in batch mode itself. Okay. So again, it's post-processing. When it comes to speed, there's no need to recompile your design. Now, this is really useful when you're actually targeting emulations or prototyping runs. And the key thing here is the flexibility. It's vendor independent. So we don't care which vendor you're getting this FSDB from, which simulator, emulator, or what prototyping utilities or tools you use. FSDB is an open format, so you have full access to the readers and the writers for FSDB. So the Assertion Manager here, when you come to the evaluation, so this is, I've read in my assertions, I'm going to select which one of them I need to apply. So you have full control. I'm not going to apply 2,000 of these assertions at one shot because I know exactly where I've made mistakes. Okay, so I can reapply selecting these assertions. And the idea is, basically getting you an FSDB file which has got purely all the assertion-based information. And this is your golden FSDB that you already had. And what Verdi will do is it will merge them as a virtual FSDB containing both your assertions and your golden database or golden design knowledge inside it. Okay. So it reduces time, quickest way to get your assertion results, and vendor independent. So all in all, it's basically that's just a repeat of the slide that I've already spoken about. So the idea here is, writing assertions is a good thing. Finds the problems, the issues in your designs. Having a methodology which is transparent or independent of any of the vendors or the flows would help. Having a common platform definitely helps. And if you can speed up the iteration in qualifying after writing new assertions, then that's certainly something that you should be making use of. That's it.
Okay, thank you, Ajay. Thanks. Any questions? Any questions from Bristol? No. Just quickly go to our... it's okay. So is there any questions from Grenoble? Matthew?
No, no question from Grenoble.
Okay, Pierre, Sophia? No, we don't. Okay, thank you, Pierre. Ashish, Imagination?
You're all right. Yeah, we don't have any questions. Thanks, Mike.
Okay, that brings us to the end. So thank you very much, Ajay. Thank you.